All right, this is for particle in a box with clay ions. So as a reminder, very quickly, particle in an infinite well or particle in a box. We have a box that runs from 0 to x, from 0 to a. Along the x direction, it's one-dimensional. My graph here, our box length is 0.01 units long, whatever distance units we happen to be using. We get energy levels by solving the Schrodinger equation from this. So the energy levels are given by n squared, h squared over 8ma squared, where n is the quantum number, n equals 1, 2, 3, 4, 5, etc. H is Planck's constant, m is the mass of the particle, usually we use an electron. And then for the purposes of this experiment, the box length is what we're focusing on for the most part. So A here is the box length. And you can see I have graphed a couple of energy levels as you go up, 1, 2, 5, 10, and 11, starting at the bottom and going up. And we see because we have the n squared in the numerator, that as n goes up, the spacing between adjacent levels increases. So the difference between 1 and 2, for example, is much smaller than the difference between 10 and 11 at the top. The other thing that you, of course, want to remember about particle in a box is, in general, we're talking about very small boxes. And since we're usually talking about electrons as our particles, the mass of the electron is very small. So 10 to the minus 31 kilograms, right, which is tiny. But the boxes are usually equally small, so the energies that you get out are going to be very small in SI units. So small that if you look at the y-axis here, everything is 0. It's not actually 0, it's just truncating the numbers to the point where we can't see them, but they're 10 to the minus 20-something joules typically. If we change the box length, that's going to change the spacing of the energy levels, right? So the box length is in the denominator of our energy expression. If I use a box length of 1 nanometer, we get the panel on the left. If we use the box length of 0.8 nanometers, we get the panel on the right. So I've adjusted A in the calculations, but I've also changed the width of the graph so that it matches. So the graph on the right, if you were to slide it over on the left, would just extend to the 0.8 nanometer point. And you can see, certainly by comparing colors, that if we squeeze the box, if we shorten the box, the spacing between energy levels goes up. And the way I like to think about this trend is to think about this rainbow jello salad thing, right? So you've got a bunch of different colors of jello, and there's kind of like a cream cheesy layer in there. I like to think of those as the energy levels. So where the color changes, that's the energy level. And it's jello though, so what happens when you squish it, if you compress it, sort of press on it? Well, the layers get thicker, right? It's taller, the layers get thicker. We can see that here on the left. If I look at this green layer, including the white part of the green layer, that's the bracket I have. If I look over on the right, that's the same bracket. But if I compare the thickness of that layer on the right, it's actually quite a bit bigger. So when the box gets smaller, the energy level spacing increases. In addition to the energy levels, of course, from solving the Schrodinger equation, we get the wave function, and that's actually one of the primary things we want out of solving the Schrodinger equation. We want the wave function. So here I have sort of the standard way to display energies and wave functions. Usually we'll display the wave function offset from 0 by the energy value, and I've color coordinated them. So the n equals 0, or n equals 1 wave function rather, now starts at the energy of E for n equals 1, which is in 0. And n equals 2 in blue is higher. It's centered about the n equals 2 energy and n equals 3 and so on. And these particle in a box wave functions, of course, are half sine waves or sine waves. So n equals 1 is a full half sine wave, n equals 2 is a full sine wave, n equals 3 is 1.5. So as we go up, the number of nodes increases, the number of half sine waves increases. Particle in a box, one of the common questions you get is, why are we doing this? Is it relevant? Well, yeah, we can see this in things. So this is some essentially microscopy for a PD20 chain, so just a chain of palladium atoms, which is a good model for particle in a box. Essentially, you can see I have the probability densities on the left, so psi star psi, because that's a better match for what we're looking at on the right, their experiment. And if you start at the top in the center and just go down, you can see that those graphs look similar to what we would get from particle in a box. You have just a single peak in the middle, and then 2 peaks, and then 3 peaks, and then 4, and then 5, and so on. As you go down the graph, which corresponds to exciting different transitions in this chain of atoms, which has a lot more particles, certainly. You can also see this a little bit less clearly, but sort of experimentally more tractable by looking at the absorption spectra of conjugated systems. So this is some diphenylpolyenes. So you have benzene groups on the end and just double bonds in between. And all that we're doing is varying the number of double bonds in between the benzenes. So changing the number of carbons in that linker. And if you measure the UV-Vis spectrum, you find that as the linker increases, the absorption shifts to the red. So to higher wavelengths. Higher wavelengths means smaller energy differences. So this is also treatable with particle in a box. So I have in blue sort of a sketch of a box over this molecule running from 0 to A, and as you add linkers, the box gets wider. As the box gets wider, you're compressing your jello, so your energy levels get closer together. As your energy levels get closer together, that means the transitions from one energy level to another takes less energy. If it takes less energy, delta E, then it's going to be lower energy, longer wavelength absorption, and that's what we see. The disadvantage to these molecules is that they are kind of obnoxiously expensive. So we're not going to use those in our experiment, and actually we're going to use something that is a little bit more straightforward. We're going to use graphite and laser to make polyions. So just chains of acetylenes capped with hydrogens. And here is the mechanism, essentially, or the general mechanism from this ChemPhysLet article, 2002. Graphite plus a couple of photons, NH-nu, to give you Cm, where m is greater than or equal to 1, plus another C, and you keep building these up, and eventually add terminal hydrogens, and you get some sort of polyion chain of alkynes. It's a sort of ridiculously simple experimental procedure. Take graphite, put in front of laser, wait, and this happens. Polyions are good for particle in a box, so here it is the calculated, I think this is the HOMO for this C6H2. So we have a lovely pi orbital that extends across all of the carbons. And if we look at what that might correspond to in the particle in a box picture, this is for a box of the size 3 randomly. There's a wave function. That's the n equals 3 wave function. And you can see if I look at the red lobes, that looks remarkably, or it tracks very nicely the particle in a box wave function, with the ends of the box being at the ends of my molecule here. So that's the model we're going to use for this system. We have a couple of practical considerations. We're using the laser, and this is it's a class 4 laser. It's not something that we can be terribly casual about. So make sure that you are reading the safety guidelines for the laser. That's in the laser instructions. Make sure that you're following those, wearing goggles, being careful about beam management, and being generally aware of what you're doing. You should be fine with that. The other thing to keep in mind is our cuvettes, especially those that we are using to get down into the UV for our absorption spectra, are pricey. So this set is easily over $100. They should only ever be in their little case or a cuvette rack or a cuvette holder. They should never be placed on a benchtop or a tabletop, just on the surface, because they are ridiculously easy to knock over. And when you knock them over, they crack or just break entirely. So don't do that. We have these lovely cuvette racks that we have purchased. They're great. They're much more stable than a tabletop. Make sure that you are using those. This, if you've read the instructions, this doesn't have a report associated with it, just the questions at the end, so it's a worksheet essentially to go along with the computational chemistry 1 weeker. So this is a 1 week experiment, as is the computation. We just sort of alternate those. All right, good luck. Let me know if you have questions.